In this video we're going to look at line shapes and how line shapes relate to certain types of data. We're going to focus on this silicon 2p on the basis that it is a pair of peaks, and we know the ratio of these peaks because of the physics of silicon and the p orbital, so these should be in the ratio of roughly 2 to 1. We also have a semiconductor, so we have a step in the background. It is also clear from the silicon 2p 1/2 peak that there is some form of asymmetry that is evident in this particular peak, and we anticipate that the 3/2 peak will have a similar sort of asymmetry. So what we would like to do is construct a pair of peaks that will return the correct ratio and fit the data in the sense of a figure of merit, such as a chi-square or an RMS. A peak model is defined using the quantification parameters dialog window. The regions property page allows us to define a background, whereas the components representing peaks within a peak model are defined on the components property page. And once we've defined these, we're going to use the test peak model button in order to investigate the best possible line shape for these data. Before constructing a peak model for these data, what we need to do is just verify that we understand what we've got. So we think we've got a silicon wafer that is clean, and these represent elemental silicon peaks. So one way of investigating this is to compare these data against other data that have known characteristics. And in this case I'm comparing the high resolution data that was the elemental silicon peaks against a peak that was measured from a silicon wafer with an oxide film. And if I just expand this, we can see that there's a shape here that represents an oxide, and we also see that the data has elemental silicon, and we can see that the resolution of the elemental silicon when we have this oxide is not as good as the blue spectrum, and this is because these were measured using different operating modes. So the line shapes between these spectra will be slightly different due to the operating modes. What this does show us is that we have a good valley between these doublet peaks, indicating that we really have a reasonable energy resolution, and that if this is an oxide peak, then the blue spectrum does not indicate there is any significant amount of oxygen that is associated with this region here that we would expect to be rising as a consequence of this oxide peak. So finally, let's just do a comparison against another spectrum, and this one is thick oxide on a silicon wafer, so thick that we see almost no evidence of the elemental silicon, and we simply see an oxide peak, and its position and its shape are very similar to this thin film. So it looks like the blue spectrum is indeed from elemental silicon, and there's no oxide that would be associated with a film of silicon oxide on this wafer. And one of the reasons these data are so good in terms of energy resolution is that sensitivity has been sacrificed in order to get a better image of what these peaks ought to look like. So the data are collected using parse energy 5, which is a low parse energy with good energy resolution, but in addition it's been measured using a field of view 2 operating mode, which reduces the area analyzed, and further there's a 55 micron selected area aperture that is further restricting the signal entering the hemispherical analyzer. So all of these together have produced a pair of peaks that are well resolved, and we've had to collect for a long time to make up for the fact that the sensitivity has been reduced, so the count rate is relatively low, but the intensity is still relatively high enough that the signal to noise is very good. The first step in making a peak model is to create a background. I've introduced a U3 2-gar background, and this allows a smooth variation of signal beneath these photoemission peaks. I'm also adjusting the end limit, and the reason that I've done this is because you can see some kind of oscillation here that seems different from the rest of the noise in the background. So this is either the start of some kind of oxygen signal oxide of silicon, or potentially this is the start of the scan, so this could be a settling of the instrument and some type of systematic error has accumulated here because of the long acquisition time. So I'm just going to similarly adjust the other end, and this gives a background upon which I'm about to add component peaks, and then the component peaks will fit in the context of this background. The next step is to add a pair of component peaks. So on the components property page, if we press create twice, then a pair of line shapes have been selected based on the element library, and if we say fit, we end up with a peak fit. The question is whether this is a suitable peak model for these data, and simply by inspection you can see that there's a signal that is not accounted for by these two symmetrical peaks. To help assess the peak model, we'll add a table to these data, an annotation table that will provide information about the peak model. So we'll include the line shape, we don't need the full width half maximum, and we don't need the area, we'll keep the percent area, the ratio. So these represent the type of information we'd like added to the display, and at this point I think that's good enough, so I'll say apply. This allows us to see that we've got two peaks and the color is indicated as part of the table. We've got the position, the fact that we have two identical symmetrical line shapes, the relative sensitivity factor, that'll come in useful a bit later, and the percent area, which for these two peaks ought to be 66.6 to 33.3. That is in the sense that these are two peaks from a p orbital, so we expect them in the ratio close to 2 to 1. So we can already see that this is not the case. When we alter the line shape in a peak model, we alter the relationship between the parameters, and you end up with a different percent area quite often. So we'll start off by adjusting the Gaussian contribution, and we'll set the Lorentzian contribution to be a full Lorentzian, and I'll copy these parameters to the other line shape using the hash that'll update all components with the same component index. So when I press yes, then we end up with the same line shape for both of these components, and you can see here that the component index parameter for both of these components is set to -1, and that's why both were updated. And this will also be important when we do other changes to these line shapes that are based on the test peak model button. So in the first instance we'll just say fit, and when we say fit with the more Lorentzian like Voigt function, despite having a poor approximation here, the percent area has moved in the right direction, that we're heading towards 2 to 1. Previously it was 60 to 40. So this is a starting point, and we can now try and adjust these line shapes together using this test peak model button. So if I now select here a range and I make this 100, 400, and I put these two numbers within square brackets, then this represents an interval over which this parameter will be varied when the data in the active tile is copied to a new file and then refitted with a range of different line shapes. So when I say OK, it tells me that I'm going to apply scan to all components with the same component index, and that's why the component index was important, and it's indicating we're going to generate a scan for the silicon 2p with the LA line shape. So I'll say yes. And then after a period of time, a new file is created, and the new file contains a figure of merit plot, so we can see how the residual standard deviation, or the RMS, is changing as a function of that line shape parameter, and also the data has been copied multiple times and fitted using the different line shapes. So it started with 100 and then it's incrementing so that we can step through and see how the line shape parameter has altered the shape and the fit of these data with these two line shapes. So at this point you can see that regardless of what I do, I cannot improve the line shape simply by adjusting a Gaussian contribution to a LA line shape that will accommodate both the missing signal here and the apparent gain of signal over here if we use these line shapes. So what I'm going to do is use an asymmetric line shape that will move signal from the higher energy side of a peak to the lower energy side of a peak. So returning to the data file, we can then perform a new fit based on a different line shape. So this one is a TLA line shape, and this is based on an LA line shape, except for it has another parameter, and this parameter is a measure of asymmetry. So when I press return here, I'll put a hash so I copy it to both, we can now see that the peak shapes have changed, and if I say fit, we see that we have a shape that is more asymmetrical, and remarkably enough you can now see that the percent area is almost exactly what we would expect for a pair of p orbital peaks. Now if I have asymmetry and the line shapes are extending in this direction and also potentially in this direction due to Lorentzian-like terms, then what I ought to do is consider the endpoints of this background. So I'm just going to make an adjustment here and here and say fit again. So let's now have a look at this and see the residual. So you can see now the residual is indicating that if there's a problem, the problem lies here in terms of fitting the data. In terms of the area is very good. So we need to find a line shape that fits these data and also produces an area that makes sense in terms of the physics for these two peaks. So now let's try again, and we will alter the Gaussian contribution. So let's say from 120 to 400. And this is going to perform a scan of the Gaussian convolution with the LA line shape that is adjusted for this asymmetry parameter. And when I say OK, a new scan will be performed. A new file is created, and this time we find there's a minimum in the figure of merit. So let's now have a look at this, and we'll scan down these spectra and look to see what kind of adjustments we've got. Well, we've got some changes in the shape here. We've also lost some of the signal here. So as we increase the Gaussian contribution, we are losing something over here. So let's now take this point, and I'm using the data file that was created from the original file as part of the scan because these are the same data. So what I can do is now make a new scan on the basis of this one, where I'll adjust now the asymmetry parameter. So I put in square brackets and I'll make this up to say 16 and apply. And let's have a look at the figure of merit. Now this is a minimum, but it seems to be quite a broad minimum. Let's have a look at what the data actually looks like. And I'm looking at the area as well as the figure of merit. So the figure of merit is quite broad in terms of fitting the data, and we end up with a minimum. So let's just do one more scan that is based on the scan of the Gaussian contribution. This time let's take a 10% interval, and having performed such a scan, Let's have a look at the figure of merit, and again you can see there's a minimum in it. So where was that minimum? Well, it was fairly close to the start, and we end up with a value for the area that looks very good, and we've got a very good residual standard deviation. So just on the basis of the residual standard deviation, I would not accept this as a peak fit. The fact that we're getting something close to what we'd expect for a pair of doublet peaks, well, that's much more powerful than the residual standard deviation. So let's just finally look at this in terms of Schofield cross sections. So I'm going to now update the relative sensitivity factor for these two individual doublet peaks, and these are calculated by Schofield, so they give us the ratio that Schofield believes these peaks ought to be in, rather than simply using the standard 2:1 ratio. You can see now that using Schofield cross sections we have achieved a really remarkable fit to these data, and also a ratio for these peaks that makes sense, and there are no constraints in this peak model other than the line shapes themselves. This particular problem has highlighted how effective the test peak model approach can be. However, it's really important to appreciate that what we're doing is effectively optimizing the line shape parameters, and so the shape is being determined by a combination of the residual standard deviation and some physical property. If we do not have a physical property that relates these peaks, and if we don't have data of such high quality and shape that we see here that has guided the analysis, then simply optimizing line shapes is quite a dangerous operation to perform, and even though you can obtain a very good residual, you may not end up with good science.